Okay, so let's update your Chapter 7 learning log. So you're going to first take this page and put it in your learning log. Let's go ahead and take a look at the different learning targets. So by the end of this chapter, you should be through these 7 steps. You should be able to evaluate an exponential function. So if you're given an exponential function and told to find a certain amount for x is equal to 10 or whatever, you should be able to apply word of operations and do that. Just remember to apply the exponent first and then multiply by the a value. So like if you got a times b to the power of x, and you're told that x is equal to, say, 10 or whatever, make sure you do the exponent first before multiplying. Use exponential functions to solve problems. The majority of our problems have really been with a lot of the finance stuff where it's growing by a certain percentage. We've also done some problems with decay where we've taken an initial amount and used a multiplier. Find the equations for exponential functions. Today in class, or in 716, you should be given a table, able to come up with the exponential function, a graph, you should be able to find the exponential function, and if you're given a situation, okay, you should be able to pull out what the initial value is and the growth. Step graphs were sort of a little aside. You saw those in the gizmos. There is going to be one on your homework you're going to try to do, and there's some notes on that. I also posted a video in your homework for tonight that goes over how to make one of those. Okay, we haven't gotten to simplifying rational exponents. That's coming. We haven't figured out how to algebraically solve a system yet, and we haven't written them given 2 points. We'll kind of have a formula that we'll be using for that. Okay. All right. So appreciation means when, in finance, when something is growing in value versus depreciation. A lot of times that's like an automobile might depreciate over time. It's just worth less. An asymptote, there are some notes that we'll see about that in a minute. Exponential function. We've been, obviously, that's what the whole unit about. Half-life, we talked a little bit about where that carbon dating. Initial value is how much you start with at your zero value. Multiplier is basically like our b value, what we multiply by to get to the next whole value of x. Parameter, a and b are parameters, so once we come up with our equation, those are no longer variables. We'll have to be doing something with roots a little bit later once we talk about rational exponents. Step function, you'll see some notes on that in a minute. Compound interest, all the gizmo finance stuff that we've been doing. And then fractional exponents are coming, so you probably don't know those yet. And then you should know what an exponent is. Okay, so, and again, these are in the glossary of your book if you wanted to go into more detail what any of those things are. Okay. All right, so then you need to take some notes on this next part. So can you guys go ahead and entitle this part Investigating y equals a times b to the x. Okay, so that's how we kind of started this whole unit. Okay, so let's first just take a look at, look at y equals b to the x. So that's how we started this whole unit. And note that b must be positive. Okay, so remember, if b were 0 or a negative value, if b were 0, then the negative powers didn't work because you couldn't take and divide by 0. And if that base were negative, the result would find to be 10 would depend on what x is. Okay, so like if I took -2 to the power of 3, it's going to be a negative value, but if I took it to the power of 4, it's going to be positive. So those negative bases or zero are sort of not part of being exponential. Okay, so we explored that a bit. Okay. So must be positive to be considered exponential. Okay, so and if b ended up being greater than 1, okay, and I guess also our a value is positive at this point, okay, the graph ended up looking like this, okay? If our base was between 0 and 1, okay, our graph, and our a value was positive, our graph ended up going like this, okay? And if b was equal to 1, then our graph just went straight across. Okay, so the multiplier is just 1 each time. Okay, so if we start with a positive a value right here, multiplying by more than 1 is going to make it grow. Something between 0 and 1 is going to make it decay. Okay, and just 1 would make it straight across. Okay, so now consider y equals a times b to the power of x. Okay, so what is the impact of a? Okay, so we should have seen from our exploring that a controls the y-intercept. Okay, of the graph. So in a curve kind of like this. At this point right here would be 0a. Okay, so it is possible that if a is a negative number, it's going to touch down here. And in that case, the curve would totally be below the x-axis, okay? So a couple things to keep in mind. B always has to be more than 0. A can be positive or negative. That's going to kind of control here. The graph is either going to be completely above the x-axis or completely below. Okay, so it's not going to cross over to the other side. Okay, so that can't happen with an exponential. Okay, graphs with asymptotes. So let's go ahead and stick this paper in there. Okay. So I think the big idea is when you'll be learning a lot more about asymptotes in a later course, but just with an introduction to it right now. I think the big thing is that we're looking at after you read over this is that in a exponential, the asymptote happens at, so let's say I've got y equals a times b to the x. If a is positive and it's over here, it's going to have an asymptote at, okay, and that would be a negative b right here. So that's going to be the asymptote, okay, meaning it's going to get infinitely close to it, okay, as we get larger and larger and larger, but it's never going to touch that, okay. Now, if we would have taken y equals a times b to the x and added some c value, like added 3 or something, then the asymptote, okay, would be whatever that c value is that we added up, okay? So it's possible that the asymptote is not here, but that's just we added something at the end, okay, which we really did not play around with in this unit. We just focused on this. So with this being the exponentials that we explored, the idea of the asymptote is that it's the x-axis, okay? The graph is going to get infinitely close to it, or if b value is positive, it would, the infinitely close to it would be as x gets smaller and smaller, okay? So it's a line that the graph gets close to but does not cross is what an asymptote is. A funny word, huh? All right, then compound interest. Okay. All right, so This was part of the gizmo activity. We did not spend much time talking about simple interest. Okay, simple interest would be if the interest didn't compound, if you didn't get interest on your interest. So if, for instance, you got 3% just simple interest, as like in this scenario, each year you would just get 3% of your initial balance. You would not get interest on your interest. Almost every bank or any loan you're going to take out does compound interest, okay, where you earn interest off of the interest that you've just gotten, okay? So if we look at this scenario, this is starting with $2,500, growing at 3% per year, okay? And then we also looked at what if it's compounded more frequently than that, okay? So if that 3% was compounded monthly, you're going to divide your 3% by the number of months per year, okay, which 12, obviously. And then that's going to be kind of your new rate, okay? And then when you look at the power, you might have to be careful because if it gives you after a number of years, you might have to adjust that. Okay, so in general, we figured out from the gizmo, the formula for these were your bank balance is equal to the principal, how much you start with, times 1 plus, and then whatever the annual percentage rate is, okay? You're going to take and divide that by the number of times it's compounded per year, okay? So if it's semi-annually, you divide your rate by 2. If it is quarterly, you divide your rate by 4. If it is monthly, you divide it by 12. If it's daily, divide by 365. Okay, so you're going to take your rate and divide it by that before you add it to the 1 to make it grow. And then your exponent, if it's given in years and it's more than just once per year, you need to take the years times the number of times per year. Okay, so like let's say it's compounded twice a year, and 5 years later, you want to know how much you have, you're going to use an exponent of 10 there. Okay. All right, step functions. We did a little bit with step functions on the gizmo. You found out that your bank balance basically stayed the same amount until the end of that time period, whether it was quarterly or monthly or whatever, and then they'd add the interest, so it'd stay that same balance until boom, they added the interest again. Okay, that's what a step function is. Okay, let's look at this example of one. So the graph below models a situation in which a tour bus company has buses that can each hold up to 20 passengers with 5 available buses, okay? So if it can hold 20 passengers, how many buses would you need for up to 20 people, okay? So do you see how there's like if this was zoomed in better, okay, this should be, and really an open dot here, okay, if you have no people, you don't need any buses, and then it's going to be closed here and then with a closed dot here. Okay, so if you got 20 people, you can fit them all in the bus, but as soon as you go over to 20, this would be open and then closed on this end. Okay, open and then closed on this end. Okay, now I'm actually not crazy about this book's example because really it probably should be dots in here, not a line, because this is really not continuous between here, but oh well, we'll just go with it. So open, and then close to here, open, and then close to here, okay? So like a better example might have been if you're mailing a package out, and this would be the number of ounces that your package is, and then how much it costs. So a lot of times there's a certain cost between a certain range of weight. And then once you up that amount of weight, then the cost goes up. Okay, so that would be a step function. Okay. All right. And I think that's all we're going to put in our notes. I know you've got an extra sheet of paper, but just to save time, we're going to hold that till later. So if you want to just go ahead and just stick it in your notebook for now, we'll take some notes on that when we finish up the rest of this chapter. Okay.